Welcome to today's lecture about remote sensing of tropospheric trace gas concentrations. My name is Torbjörn Tagesson, and I'm an assistant professor here at Copenhagen University, but I also work as a researcher at Lund University. I am normally actually not really working with remote sensing of the atmosphere. I am more focusing on remote sensing of the vegetation, and more specifically about the exchange of carbon dioxide between the atmosphere and the ground. So I try to create models based on field observations of carbon dioxide exchange, and then I relate those to satellite observations to create models to spatially extrapolate these measurements globally, locally, and regionally. That was a bit about me, but back to the lecture of today. So today we're going to talk about remote sensing of tropospheric trace gas concentrations. And first, we're going to have an introduction to set the stage to so what are the physical and chemical properties of the atmosphere. Then we're going through some different trace gases that are very strong polluters of the atmosphere, and then we're going into how to measure atmospheric compositions on the ground. Then in the second part, we come into the actual remote sensing of the tropospheric trace gas concentrations. So we will start with going through some challenges in the remote sensing of tropospheric trace gases. And then we're going through the entire process of how to come from the measurements of the satellite into a final product of the tropospheric trace gas. And in our case, we will talk about the nitrogen dioxide. And then in the final part, we are going through some different satellites which are used for remote sensing of trace gas concentrations, and some different applications where atmospheric remote sensing have been used. Finally, we will go through the exercise which you are going to do on Friday. So let's start with setting the scene. In the atmosphere, there is a strong decrease in air pressure with height. And the reason for this is, of course, the gravity. That the closer to the ground, the more molecules above that is like pulled downwards from the due to the gravity, and this causes a pressure on you that is standing here on the ground. And the further up you are, the less of the molecules there are that is pressing on you, and thereby the air pressure is decreasing. And same thing then with the density, that the gravity pulls the molecules downward, and thereby there are more molecules and higher density of molecules down here in the lower part of the atmosphere compared to further up. On the other hand, temperature, it has a quite complicated profile. You can see here that in the lowest part of the atmosphere, and actually the reason the temperature profile is thereby used to separate the atmosphere into different layers, so that we have the lowest layer, troposphere, there is a certain temperature profile, and then the next layer, stratosphere, has a different temperature profile, the mesosphere, the third one, and the thermosphere, the fourth one. So this temperature profile is used to separate the atmosphere into its different layers. And then if we start then with the troposphere, the temperature and pressure is of course heavily linked, that the higher the pressure, the higher the temperature. So therefore, temperature decreases with height as air pressure is decreasing. Additionally, the sun is shining on the ground surface, which is heated up, and thereby the ground has a higher heat compared to further up. and this heat is then transported upwards. So this is two reasons which causes temperature to be higher the further down you are compared to further up. But why doesn't this then continue throughout the atmosphere? Well, when we come up here in the stratosphere, we have a different pattern. And the reason for this is that here in the upper part of the stratosphere, that's where we have the ozone layer. This is where the highest density of ozone is located. And ozone is a strong greenhouse gas, absorbing a lot of the incoming radiation, and the heat is thereby increasing with height. Then in the mesosphere, we again see the opposite pattern, and this is because then the maximum concentration of ozone is in this layer here, and then it's again decreasing with height, and thereby the temperature is also decreasing. Finally, up in the thermosphere, we are very close to space, and here it's extremely few molecules, and but the molecules that are there, they get highly energetic because of solar storms and incoming energy from the sun. So those few molecules that are there, and temperature is a measure of the movement of the molecules. They can be highly energetic because of these high energy beams coming from the sun. So therefore the temperature can be extremely high in this part. But since there are so few molecules, you wouldn't really feel it as extreme heat. But those few molecules that are there, they can be very energetic. So what do the atmosphere contain then? What is the actual chemical composition of the atmosphere? Almost all of the atmosphere is three different elements. We have nitrogen, 78%, oxygen, 21%, and argon, about 1%. So these three elements together, they constitute 99.5% of the entire atmosphere. And the remaining gases, they are called the trace gases. And this is what this lecture will be about, how to do remote sensing of some of these trace gases. And the one that is largest of these trace gases is carbon dioxide, which you of course know about. And then we have some noble gases, neon, helium, and methane, which are they are very inreactive since they are furthest out in the periodic table and they don't react with other elements. But we also have some gases which are highly reactive and thereby very important for us. So, and these are the ones we will go through now. And since some of these trace gases, they are very reactive, they can be harmful for us. So if these gases reaches above a certain level, they are considered to become an atmospheric pollution. And pollution, environmental pollution, is any release into the environment that may cause loss of Earth's ecological balance or that may lower the quality of life. So this can happen anywhere, but what we are interested in is the atmospheric pollution. And the main sources of atmospheric pollution are power plants, industries, transportation, biomass burning, and agriculture. But the sources are not only anthropogenic, they can also be natural sources, such as lightning strikes and volcanoes, and when organic material is decomposing, some of these gases can also be released, and also fires. And the main thing with atmospheric pollution is that it does not stay on one place. It can be transported all over the world, basically, so that Europe, for example, is affected by the pollution that is released in North America. the Arctic is affected by the pollution that we release here in Europe, and so on. And therefore, it's very important for us to further understand where are the main sources of this environmental pollution, since it affects our life so much, and where do they go? How are they transported across the world, and so on. And yeah, this is, of course, where remote sensing come in. We can get a further understanding of what's going on in our atmosphere. And some of the major atmospheric pollutants are sulfur dioxide, nitrogen dioxide, ozone, carbon monoxide, and greenhouse gases. And we're now going through a little bit about each and every one of them. So to start with, the oxides of sulfur. Sulfur dioxide is produced when burning fossil fuel. And so that's the main source of sulfur dioxide into the atmosphere. But there are also natural sources, and it can be emitted when organic material is decomposed in anaerobic environments, such as in wetlands. So I assume some of you, at least, have been trampling around in wetland at some point, and occasionally you can then feel that it smells a bit like rotten egg. And this is the sulfur dioxide that you really smell then. And in the past, sulfur dioxide was one of the biggest problems with when it comes to the environment here in Europe. In the 1980s, it wasn't climate change that was the big environmental problem that everybody was talking about. Back then, it was actually the forest diebacks, as you can see here in the middle. That when we burn fossil fuel and emitted this sulfur dioxide into the atmosphere, the sulfur dioxide reacted with water, and then it came down as acid rain. And this acid rain turned the soil so sour so that several forests across Europe just died. They couldn't live there anymore. And this, yeah, at first they didn't know what it was, of course, but after a while they realized that this was a big problem all over Europe. And the same thing, this acid rain also caused statues across Europe to just vanish, just like you can see down here. Another problem was also, here you have an example of salmons that's living in a lake without the problem of acidification, whereas in relation to what happened when the lake turned more and more sour due to this acid rain. So this was a big problem in Europe back in the 1980s, back up until the 1980s, in the beginning of the 90s. But then after that, there was a law that you need to have, what is it called again, catalyzers on cars, for example. So now there is a very positive trend on the amount of sulfur dioxide that is emitted into the atmosphere, which much less. And forests have returned again, and the statues have stopped vanishing, and so forth. The next air pollutant we're going to talk about are the oxides of nitrogen. And later on, when we're talking about how to convert satellite data into a product of a tropospheric trace gas, it will be the retrieval process of nitrogen dioxide that we are going to talk about. And oxides of nitrogen is a very important atmospheric air pollutant. You have probably all seen pictures of cities such as Los Angeles with these reddish brownish clouds above them. And it is then the oxides of nitrogen that gives the color to these clouds, which are called smog, smoke and fog combined. And the main sources of the oxides of nitrogen is the burning of fossil fuels, when we drive the cars in these cities, when we have the power plants that is burning coal and so on. There is a lot of oxides of nitrogen that is emitted. Boats are also heavy emitters of nitrogen dioxide. And the nitrogen dioxides, or the nitrogen oxides, they have basically the same impact on the environment like the sulfur oxides, which we were talking about before. They are a part of the acid rain, so they are causing this, causing the land to become sour and killing off the vegetation and so forth. But on top of that, it also has nitrogen is a strong fertilizer. So when this nitrogen ends up in lakes and in the oceans, they cause eutrophication, and there will be algal blooming with big impact on the lake and ocean ecosystems, of course. And the nitrogen oxides causes health problems also to us humans. It can cause asthma, and it usually causes breathing problems, for example. So this is a very harmful and important air pollutant. So it is obviously very important that we keep track of these trace gases, since they have such big impacts on the environment which we are living in and on our health as well. And one way of keeping track of this is to do in situ measurements of the concentrations of these trace gases in the air. And what we then do is that we are taking an air sample and put this air sample through a gas chromatograph or an infrared radiation sensor, and then we can estimate the exact concentration of the trace gas in that air sample. And this is of course extremely important because it gives us very accurate estimates of the concentration of the trace gas in that air sample. And we can do this continuously at the point to get long, nice temporal time series of this, such as you have probably all seen this long time series of carbon dioxide concentration from Mauna Loa, where we can get estimates of the exact concentration of carbon dioxide in air. So the strength of these in situ measurements is their simplicity and their accuracy, and that they have very high temporal resolution. However, it's expensive to do in situ measurements, and it's basically impossible to cover a larger area with these in situ measurements. So therefore, stations are very sparse. But if we want to know what's going on in a wider area, we need something else. And then, of course, this is where the remote sensing parts come in. So we can use the remote sensing to look at the spatial patterns in these trace gases, but we still are very, very dependent on these in situ measurements, because these are data that we can use to create the models that we will apply on the larger spatial scale. And we can also use these in situ observations to see if our model, remote sensing based model, are working well. Yes. So, welcome to the second part of this lecture, remote sensing of tropospheric trace gas concentrations. In this part, we're going into the actual remote sensing, which we haven't done so far. And we're going through what are the main challenges there are when we are using remote sensing to estimate trace gas concentrations. And we're also going through the entire retrieval process for how to estimate the tropospheric trace gas concentrations. So it is naturally not so that satellites, they cannot actually measure the trace gases in the atmosphere. They don't take an air sample and measure the concentration inside that air sample. What we get from the satellites is incoming radiation from the sun and then reflected radiation back from the atmosphere. And then based on these data, we need to create a model which we can convert these data into the trace gas product. But once we have this product, we have a very strong tool for getting further understanding of our Earth. Now we can get information on where are the main sources of air pollution, where are they coming from, and where is it going? If we have a main source here, maybe for example along the cities along the coast, maybe it's transported further inland instead of being blown out into the ocean. So we get some information on where is the transport, where are the air pollution transported across the Earth. And by now, we also have quite long time series of these satellites product. So we can also start to study how are the trends going in the air pollution. Do we have more air pollution today or do we have less? What impact is there if we make a political decision that from now on it's illegal to emit this pollution into the atmosphere? Then we can study, see, was there a breakpoint there? Did it have any impact or not? So this is a method or a tool to, it's a very strong tool to get further understanding on the cycles of these trace gases in the atmosphere.